And welcome to our session, Why Details and Observability Matter on AWS. My name is Morgan McLean. I'm a Director of Product Management at Splunk. Specifically, I'm responsible for much of our cross-cutting functionality in Observability Cloud, including how we get data in. I've been part of the OpenTelemetry and earlier Open Census community since the very beginning, along with Steve.
And hi, I'm Steve Flanders. I'm a Director of Engineering at Splunk, and I'm responsible for Observability GDI, or Getting Data In. I've been at Splunk for the last 2 years and came in as part of the Omnition acquisition. I've been in the monitoring and observability space for well over a decade now, and I've been involved in both the Open Census and OpenTelemetry projects since the very beginning.
So today we're going to talk about a number of things. Specifically, we're going to start with availability and why it matters, how availability impacts your development velocity and why development velocity is important, how good observability is a prerequisite to high availability and high development throughput, and how you can achieve this with OpenTelemetry and with OpenTelemetry and Splunk Observability Cloud. Users' expectations are at all-time highs. If people use various online services, including Amazon and AWS, they expect them to be highly available. And for decades, those expectations have been met. So when you have a business, no matter what your business is, and you're developing web services or client applications, your users have been trained with the various other services they use that software is meant to be highly available and high quality. And so this presents a challenge. Because your users have such high expectations, you have to rise to meet these. And if you don't, if you have poor availability, and if you have a low quality service, you will begin to lose out to your competition. Secondly, the expectations of your own staff, your own technical staff, your developers are also at all-time highs. Developers want to work in environments where they can maintain a high development velocity, where they're not constantly churning and working on outages and responding to issues at 2 in the morning because the site is down again and again. In order to maintain staff and in order to maintain a high development velocity where you can ship new features to stay in competition with your competitors and delight your customers, you also need to have high availability. You need to have highly resilient services that people enjoy working on and also that you can extend and continue to build on over time. So both of these are critical. And none of this is new, right? So observability is a prerequisite to attaining high availability. So in order to have a service that's always on, always running, highly available, in order to have a service that has high development throughput, you need to understand what is going on inside of it. This is hardly a new concept, right? One imagines, or one cannot imagine rather, a manufacturer that doesn't track its own suppliers and supply chains. That would be ridiculous. It would be prone to failure. Similarly, one cannot imagine a retailer that doesn't track its own inventory. But we're here at an Amazon conference. Can you imagine if Amazon, when you bought something, didn't have a rough idea of when it would arrive or couldn't track it when it was sent to you? No, that would be preposterous. Similarly, even in the pure software space, can you imagine in this day and age developing software with no source control? No, that would be ridiculous. Or any business that it doesn't track its finances. All of these scenarios are quite bizarre. And yet, when we think of the services that we run online, there are so many examples that you've probably experienced yourself or heard of where there's effectively no monitoring, no observability, very little ability to inspect how those services are deployed, the infrastructure they're running on, and how they interact. This needs to happen. As we go forward, if you want to have a successful web services company or even a client application company, you need to have powerful, deep, and intuitive visibility into how this works in order to stay successful. Else, you will be akin to a manufacturer that does not track its supply chain or the other examples here. And unfortunately, you'll be left behind. You'll struggle with your customers. You'll struggle with your staff. And just to set the table a bit more, we live in this very interesting era. Over time, over the last decade or so, we've seen cloud services make it very easy. So cloud service platforms like AWS and others make it very easy for you to go build your own cloud services, deploy them at extreme scale. And similarly, the actual programming paradigms and practices that we use have changed along with that. No longer do we build large monoliths that get deployed all at once, but instead we've broken up our code into different microservices. This is generally positive. I don't mean to begrudge this. It means that we can now build and maintain code and applications at a much higher scale than we could before. This is great. However, there's a cost to this, and we end up building these very complex behemoths, and indeed ones like in this example, that are deployed all over the place with different pieces of client code, code running on AWS, code running in your own data centers, code running in other clouds from SaaS services that you need to be able to understand. And as I've shown here by darkening much of the map, what's generally the case in a large enough organization is that an individual engineer or an individual even manager only really has visibility into the parts of the application or parts of their infrastructure stack that they work on directly. And yet, when there's a problem, when they're trying to, or if they're trying to extend something to work with another team or another service, these same people need to have visibility into the entire stack. This is where observability comes in. It gives you this visibility into the entire stack. And if you don't have this, that's when you end up in the cases I was describing before, like a manufacturer that doesn't have any visibility into its own supply chain. If we want to build high quality software that's highly available at scale, we need this deep understanding of all our applications and all of our infrastructure.
And we also can't expect that developers are going to actually know more than just like their own services, right? If you look at any cloud provider tech stack or even something like Kubernetes, it's a complex system. It provides a lot of functionality. It's extremely powerful, but like no one person can know and understand all of those aspects and how they're going to interact with one another. Previously, when we kind of packaged things together and kind of shipped these monoliths, maybe it was a bit easier because you can kind of controlled most of the parameters that were being specified and it's in one central place. And in those cases, maybe you kind of learned over time the behaviors of these systems and you could determine like when certain thresholds were being exceeded that you probably wanted to do something. You wanted to react to those. That was more kind of the monitoring mindset. And as Morgan was saying, like observability isn't new, like you kind of monitor your systems, but the picture that he's really articulating here of just showing like the complexity of these interactions, especially over time, a single service may have one dependency inbound today and one dependency outbound today, and tomorrow that could be 2 or 10 or 100. You're never really going to really know what these interactions are. And so you need to be able to ask basically any question of your system, and you need to be able to understand full stack, both the infrastructure components wherever it's running, as well as the applications and how they're interacting with one another as well.
And the good news is this is easier to achieve today than ever through a number of different mechanisms. The most prominent and sort of the main thing we're talking about today is OpenTelemetry. OpenTelemetry, and we'll talk about it in a moment, is a great way for you to extract the necessary information out of your applications and out of your infrastructure in order to be able to process that data and then gain vision into it. Secondly is Splunk Observability Cloud, which we'll also discuss in this presentation. Splunk Observability Cloud takes the data that you've used, that you have extracted from your applications and infrastructure with OpenTelemetry and allows you to analyze it, to inspect it, and to gain a much better understanding of everything that you've deployed, how it interacts, and how you can resolve outages or problems as they occur, or even before they occur. So let's dive a bit into OpenTelemetry. Probably the best way to break this down, because it's a large project, is to talk about the different things, different components, different artifacts that you get as an end user of OpenTelemetry if you adopt it. So we'll start with the actual components that you can deploy. So primarily, OpenTelemetry has a set of language-specific SDKs, one per language. These SDKs can be linked to your applications. They'll capture distributed traces from your applications. They'll handle context propagation. And they'll also be able to capture metrics from your application. And then finally, they give you the APIs that you need to interact with them if you want to generate any custom data. So for example, if you link the Java SDK to your application, you'll get various Java metrics and assuming you're using a supported RPC system or various sets of libraries, you'll also get distributed tracing and context propagation. But you can also use these SDKs to generate, say, a custom metric that couldn't normally be captured automatically, like daily revenue or something that's specific to your business. And so these are how you get application information out of your services with OpenTelemetry. Next, we have the OpenTelemetry collector. This is deployed typically to every host. It can also be deployed as a cluster, but more often it's to every host or to a single Kubernetes cluster. And this extracts infrastructure metrics and infrastructure logs from your various hosts. And it will also capture data from those OpenTelemetry SDKs, capture that, and then export it to your destination of choice. You can export data directly from the SDKs if you choose. Generally, people choose to send it through the collector because you need the collector there anyways to capture infrastructure information. Finally, in terms of components that you'll actually really be pushing down to your services, interacting with, configuring, we've automatic instrumentation. These are an alternative to the SDKs in most circumstances, or you can use them together. And so, for example, for Java, like I discussed earlier, as an alternative to installing the Java SDK, you can use a Java agent that gets referenced in the JVM. This is generally easier to get started with. You don't need to make any changes to your code. You don't actually need to rebuild or redeploy any services. The downside is that you can't generate any custom data with it. So if you were generating custom metrics or custom annotations for traces, you'll still need the SDK to do that. Fortunately, they work really well together. And Steve, do you want to describe the other components in OpenTelemetry?
Yeah, so really here, the way that I like to think about the project is everything that you need to deploy in your environment in order to generate, emit, process, and export the telemetry data that you care about. So, I mean, Morgan just told you about the core components, like instrumentation libraries, one per language that you care about. All major languages are supported today. And then, of course, the collector component. Now, on top of all of this, or the foundational piece of these two components is actually the specification. So there is an open standard that has been defined. This has like the API contracts or like the configuration parameters that you're using. It also has an underlying data model that is extremely flexible to support other open standards that are out there. Actually, one of the goals of OpenTelemetry is to be not just open source, but vendor agnostic. So, I mean, from a greenfield perspective, it would be great if you could just deploy all of the OpenTelemetry components that you needed to solve your business requirements. But a lot of environments today already have existing monitoring tools. Maybe you're using the open source Jaeger tracing product, or you're using Prometheus. Maybe you're using the Prometheus instrumentation libraries today. Maybe you're using Zipkin's instrumentation libraries. The good news is that OpenTelemetry supports all of these open standards as well. So you can actually receive in one format. For example, maybe I use Jaeger tracing on my Java application instead of OpenTelemetry, and I use the collector, and the collector can go ahead and emit in a different format than it was received in, which is kind of powerful. Now, this specification being an open standard is also extremely important because it provides things like data portability. One very cool aspect of the project is that it actually defines semantic conventions. Think of it as like metadata, key value pairs. So for example, if we all call like database interactions the same thing, then we can represent them and we can do things with that data, no matter which backend we send that data to. This provides flexibility and choice with what you want to do with your data. The end state here is if you deploy OpenTelemetry in your environment, you can basically move to a configuration model. If you want to send your data to a different place, you don't have to rip and replace everything, you just change your configuration. If you want to enrich the data that's being received and you want to add metadata, you can go ahead and modify the configuration. If you want to redact or remove like PII information that you notice is being passed, it's a little bit harder to like re-instrument your app, but from a collector perspective, again, through configuration, you can remove that information. So flexibility and choice every step of the way.
So it's probably best to demonstrate this with some semi-real world examples of how you would take a toy application or example application and actually instrument it for OpenTelemetry so you can capture this information for processing later in whatever system that you choose. In this example, we have an AWS EC2 VM. It's running some Linux distribution, doesn't really matter which. Could even be running Windows. OpenTelemetry supports both. On this VM, we have an instance of the JVM that's running a Java application that we have built at our own organization. This is an application that we want to get traces and metrics and everything else out of. Similarly, we also have a database running on this VM. Obviously, in most scenarios, you would have your databases separated from your application logic. They'd be running in different locations. But in this toy example, we can use this to demonstrate how you would use OpenTelemetry to capture both. So to start, you would generally deploy the OpenTelemetry collector to your app, to your virtual machine. This collector, when you include the necessary instrumentation that's also provided by the community, will then capture information from your host operating system. So this is host metrics like memory consumption, CPU consumption, disk consumption. There's a large set of them that we capture. It'll also capture host logs with the new logging functionality that is currently being added to OpenTelemetry. Next, it'll also capture metrics, and once logs are complete, logs from your Java virtual machine. Specifically, these are like core JVM metrics. So this is not your like latency metrics or anything like that that's part of your application, but these are the base sort of JVM runtime metrics. Finally, the collector will also capture relevant metrics and logs from the database that you're running on this VM. And so it'll capture all of those, and we have integrations for many, we call them prepackaged applications, but sort of many commonly used enterprise applications. So think of like MySQL and Oracle and various other types of databases that are commonly used. OpenTelemetry has the right extensions to capture data from them and process that. Next, you can deploy, as we mentioned earlier, the OpenTelemetry SDK inside of your Java application. So you go into your source, you download a new library, link this to your app, and instantiate it. And so generally, when you include the correct instrumentation, again, provided by the community, this means that you'll get distributed trace propagation, you'll get distributed traces captured, and you'll generate metrics for various endpoints and basically request metrics from this application. And as I mentioned earlier, as an alternative or a complement, instead of the SDK, instead of rebuilding and redeploying your application, you could also deploy the OpenTelemetry Java instrumentation. Regardless of which one you use, they send their captured data to the OpenTelemetry collector, which then sends it to your destination of choice. That destination might be Splunk Observability Cloud, might be others. You can export your data to as many different locations as you want simultaneously. And Steve, did you want to talk about the different distributions that are available?
Yeah, so the open source community provides a lot of rich integrations for you out of the box and the ability to basically customize that how you see fit. At the end of the day, though, you probably want to deploy this in your environment, you want it to roll out into your production environment, and you want to send that data to one or possibly multiple different backends in order to kind of consume that data back out. When you do that, you're looking for a few things. One is, it's an open source project, but you're going to need enterprise support. You're going to need the ability of calling someone up and asking for help if anything is going wrong, or you want like an enhancement request to it and you just kind of want someone to work with. Distributions are one way to provide this. Basically, all major cloud providers and all major vendors that are kind of in this space are offering what's called a distribution. A distribution is not a fork of the repository, and there's a very clear distinction here. A distribution means that you're pulling in the OpenTelemetry project and then you're wrapping it in some way in order to provide support. So some of the things this could provide is kind of ease of use, maybe some environmental variables or other configuration that just makes it a lot easier to get started to send your data to a specific destination. It can also include support. So a way of ensuring that if you roll this out in production and there's some sort of issue, that you know who you can contact in order to get support for it. The idea is not to diverge, so it's still completely OpenTelemetry compatible, and if you're more comfortable just using pure upstream, you can as well. Even in OpenTelemetry, there's kind of a notion of distributions as well. There's often what's called a core repository, the primary repository that has the base functionality. The idea there is typically to minimize the surface, like the API surface for the software developers out there, as much as possible, and then provide kind of extension points. Many of these repositories also offer a contrib or a community-based repository as well in OpenTelemetry. And these are things that are not core to the project and may not be applicable to everyone, but provide very nice extension points. The contrib repositories are basically a distribution. So they pull in core and then they add some modifications to it. Vendors and cloud providers also offer these distributions. You can learn more about this by taking a look at opentelemetry.io.
And one thing I want to add is these distributions, whoever you get them from, they're generally just snapshots of core with community contributed other content put in. So you can contrast this to another open source project like Linux, obviously a much even larger project than OpenTelemetry by many orders of magnitude. But in Linux, as a user, you generally use a distribution of Linux like Ubuntu, for example, or various others that uses the core Linux kernel, but has a lot of extra content on sort of tacked on or included in it because you can't just use the kernel on its own. With OpenTelemetry, the distributions are generally pretty close to being snapshots of the open source project because we focus so much on the open source project of making it batteries included, so to speak, or including all of the things that people need right out of the box when they use it. So generally, these are just basically bundles of OpenTelemetry and other instrumentation that's also part of OpenTelemetry in a single package that's supported by a vendor.
I'll add one more thing for those that are kind of comfortable in the cloud native world or the CNCF, right? Most people have heard of Kubernetes these days. If you think about EKS, for example, that is a distribution of Kubernetes. So this is pretty common in open source, especially for complex projects, with the idea being to provide what you need that's fully compatible and provides the features and functionalities with the ease of use and the best support for your use cases.
All right, so the best way to demonstrate what we've talked about is to show it actually in action. So we're going to show two demos now. The first is of the Splunk Observability Cloud. We're going to give you a walkthrough of how you can use the information extracted from an application and infrastructure with OpenTelemetry to solve real-world problems, particularly taking advantage of some of the correlations that OpenTelemetry provides between different types of data. Following that, we'll have a demo of how easy it is to capture data from an application and from infrastructure with OpenTelemetry. So we'll actually show you how quickly you can instrument your application and infrastructure to extract that information out. So let's get started with the first demo of Splunk Observability Cloud. Now we're going to use Splunk Observability Cloud to break down a real-world scenario. So in a test environment, I've gone and deployed Hipster Shop. This is a commonly used demo that gets deployed into Kubernetes environments. In this case, we have it running on AWS, originally created at Google, though it's used across the industry now. The beauty of this demo environment is that it's a giant polyglot architecture. So we have 10 to 15 different e-commerce services. They're real, their ability to actually transact on my credit card, but they are built sort of in the structure and layout that you would generally see for an e-commerce application. They're written in a variety of different languages. They use different RPC systems. We have a variety of different databases back in the data. So it's a great real-world example of the types of environments that customers and end users rely on every single day. Splunk Observability Cloud has a number of different ways to break down or to visualize our data. We have APM, an application-centric view, RUM, which is a client performance-centric view, infrastructure monitoring, which just allows us to generate dashboards and navigate our infrastructure of a number of great predefined views, and a variety of others. In particular, in this case, we're going to use APM to begin our journey, though we will end up in many of these other pillars. And that's because we're investigating very slow checkout events that our customers have complained about. So let's dive into APM. Now that we're in APM, we can quickly see an overview of the different services that we've deployed. This is broken down by error rate and latency for each service. We also have breakdowns for what we call business workflows. These are a construct that we use that are by default capture various endpoints and gRPC methods and the sort of interactions we have between services. You can also define your own custom business workflows in Observability Cloud. If we scroll down, we see a slightly more detailed breakdown of each service, again by latency and error rate and throughput. But because we're fairly unfamiliar with this scenario, I actually want to dive into a topology map that shows my different services and how they interact with each other. So if one click, I'm launched into our application topology view. I'll bring up the legend so people can understand what they're looking at. And this topology view shows us the different interactions between our services. Additionally, it shows the relative size of these services by throughput, as well as the error rates of these services and any issues occurring along these interactions. And so from this view, we can immediately see some of the issues. We have about 3 seconds of latency between our front end and checkout service, and this is usually measured at the, not necessarily the 50th percentile latency. I think in most cases we're measuring about the 90th percentile latency here, and we can also mouse over services and see previews of them. You can also click on a service to interact with it to see better breakdowns here on the right. But because we've been informed and because we can visually see that there's so many issues between our front end and checkout service, we're actually going to further filter down this map. And so we're going to do that by filtering for the checkout business workflow. So this here will allow us to filter down for all of the events that are caused by a user posting to the checkout endpoint of our front end service. Now the nice thing about application performance management views is that they're generated from distributed traces. So even though we're filtering for something that occurs on the front end, through the traces generated on the front end service, we can understand their impact all the way down to our individual databases. And so just to make that super clear, what you're viewing here now is a graph that's been pruned at every single level for just a piece of metadata or for an user action that took place at the head of the graph. And so for example, the latency that you see here between the cart service and this Postgres database doesn't represent all of the traffic between the cart service and the Postgres database, because that wouldn't necessarily be useful to us. But because we've used OpenTelemetry to extract traces and apply metadata, we've actually filtered this down just to the interactions between the cart service and Postgres database that were caused by checkout interactions just to the front-end service. That is the power you get with distributed tracing from OpenTelemetry. And right here we can see that the problem is in fact worse than we first suspected. We've got about 7 seconds of latency from external clients to the front end for these checkout events. And indeed, effectively all of that latency is caused from the front-end service talking to the checkout service. From here, though, in the graph, we can form a few hypotheses without even having to dive into individual distributed traces. And 2 things stand out immediately. The checkout service, while the latency to its subordinates don't add up to 7 seconds, they're still quite high. And so we've got about half a second of latency between the checkout service and cart service on these checkout events, and another half second of latency from the checkout service to the payment service. So right away, we've learned a few things. First off, something interesting is happening here. The downstream latency beneath checkout is high, unacceptably high, but doesn't nearly account for the extremely high latency from the front end to the checkout service. That's interesting, so we're going to have to dive into that. Secondly, we need to investigate the checkout service communicating with the payment service down here, and the checkout service communicating with the cart service up here. For these cart service interactions, we can already form another even stronger hypothesis, because the cart service only talks downstream to two databases. And so if we look at the interactions between the cart service and our Redis database, these are extremely fast, just short of a millisecond. But when our cart service talks to our Postgres database, we've got, again, about half a second of latency. And so right away we know we need to investigate this. We should file a ticket, have an engineering team go and pick it up, or our database administration team, and find out what's causing this Postgres database to be slow so we can speed that up. So right away we've formed a very strong hypothesis and taken an action. But still we haven't solved the problem. And so when you look at the checkout service calling to the payment service, we see a very high number of errors. That's interestingly. Similarly, what's similarly interesting is we don't see errors propagating up from the checkout service, but we see an even higher latency. So this is something that we want to dive into even deeper. There's a few things we can do here. And so first, I'm going to click on the checkout service to interact with it to see some more information about the service on the right-hand side of the pane. I can also launch into one of these dashboards. This is an automatically generated dashboard for every single service that Observability Cloud generates from OpenTelemetry data. And so much of this is just data that we would have seen on the other page, but we can also continue to scroll down. And because we also correlate this with the host and infrastructure metrics for the hosts that are backing this service. And nothing really here jumps out, right? If there was an infrastructure issue, we'd expect to see high CPU or extraordinarily high memory usage. Things here appear to be in pretty normal parameters. And so there's nothing to be too concerned about. If we continue to scroll down, we actually pull in specific Kubernetes metrics. Again, nothing here screams at us that there's an issue. We're not seeing constant out-of-memory issues. In fact, this service is using very little CPU. These pods are arguably underutilized. And so from this, we can, I think, quite likely rule out that this is not an infrastructure issue that's happening here. So we need to dive further into the application. And so in this case, because we have these errors, there's two paths we could follow. The first would be look at logs from the payment service that are attached to these requests. And we can do that. If I click down here, we jump straight into our log service, our log viewer, and we could view these errors in the log viewer. That won't necessarily help us because there's another tool that we can use that will give us even greater context and greater insight into what's happening here. And those are distributed traces. And so while we've avoided thus far going in directly into distributed traces for this investigation, and we formed one very strong hypothesis about what one of the root causes may be, we do need to dive into them to find out what is going on with these errors and how that's leading to higher latency higher up the stack. And so I've already selected a trace here, but if we click here, we can see a list of distributed traces to select along with their duration and the services that they impact. I've already gone through and selected one that's, I think, highly demonstrative of what's happening here. And so this trace, again, shows the entire request all the way from the front-end client request all the way down to individual databases and other endpoints that get called as a result of it. But in here, we can see where these errors are. And these are related to the checkout service calling the payment service. And so this is interesting. We can see this chain of requests is repeated about 3 times here before it actually succeeds without an error. This is interesting. So it appears that our checkout service is calling the payment service. An error happens. The checkout service then tries again to call the payment service. An error happens. The checkout service then tries a 3rd time to call the payment service. An error happens. And on the 4th request, on the 4th attempt, the request actually proceeds. And so with this single trace, we can form now an even stronger hypothesis about what's happening here. We have some kind of intermittent error happening on the payment service that is impacting the performance of the checkout service as it continually retries to contact the payment service. And so to dive into to get more details about this error, we can actually click here and view the logs that are generated as a result of this individual trace. So again, here we're looking at logs across all of our various services that are correlated with this trace. As I mentioned earlier, we could have gone into a logs investigation for the payment service. That would have been a different way to solve this. But this way, by following the traces, I think gives us a bit more specificity, a bit more confidence in what we're looking at. And so if I click here, I can filter this log down just to see errors because we already know that we want to look at these. Now that the filter is applied, as I scroll down, I can click on the individual log statement and view more about it. And right away, we see something that allows us to validate our hypothesis that these errors that we're experiencing that are causing this slowness are that we failed payment processing through our payment API due to an invalid API token. suddenly everything makes sense. And so if we go back to this view of what's happening here, we can explain it from everything that we've learned. Our clients call in for checkout to the front-end service. That gets past the checkout service. The checkout service makes some kind of calls to this Postgres database. Those are relatively slow, but they're not the main cause of our slowness. Still, they're too slow. They need to be investigated. However, the main cause is when the checkout service calls the payment service calls Buttercup Payments, and for many of these requests, it's using an invalid API token. That's causing these requests to get reset and reset and reset as the checkout service retries the payment service, which then retries Buttercup Payments until they succeed. This explains why this is slow. It also explains why these average requests here, while unacceptably slow, certainly don't add up to the extreme latency we're seeing over here on the front-end service calling the checkout service. Explains that. And finally, it explains why these errors between checkout and payment are not being bubbled up to our users. They were complaining about slowness, but on errors, that's reflected here. And so, in just the course of a few minutes, we've used Splunk Observability Cloud to analyze the data that we've received from OpenTelemetry and form an incredibly strong conclusion about what's going on inside of our applications. We've ruled out the possibility of an infrastructure issue, and we were able to do that quickly with our incredible correlations that we have in our product between application telemetry and infrastructure telemetry. And indeed, we've used the highly structured highly structured nature of these traces to slice our quickly winnow down our view of our application and see where the problems arose. And we've related it back to this database error, to database latency rather, and errors inside the payment service. So with that, we're all done, and we'll move on to Steve, who's going to give a demonstration of how easy it is to get started with OpenTelemetry.
All right, so you just saw a demo of Splunk Observability Cloud and how easy it is to really take all of this data and provide rich insights, visibility, and really be able to answer any question that you want. Next, we're going to show you a demo on how you can actually get started with OpenTelemetry. We want to show you how you can instrument an application to actually generate and emit this telemetry data, as well as deploying the collector and how it can be used to collect both metric information, log information, and receive trace information as well. Let's get started. I want to first show you how you can get started instrumenting your applications. To do this, I'm going to use an open source microservices demo application. This is basically a web store, and it's made up of multiple different services. It's basically a microservices architecture, and it's actually a polyglot architecture. So while it has multiple services that talk to each other, those services are written in different languages. So for example, here, if we look in the source directory, you'll see all the different services that exist. And if we look at, say, the add service, you can see pretty quickly here, this is a Java application. You can see Gradle files. We could also take a look at, for example, the cart service. This looks like a .NET application. So as you can see, multiple different applications you can play with. And the question becomes, well, how can I get started with OpenTelemetry and actually instrument the apps that I care about? Now, this microservices application is actually more cloud native. It offers Kubernetes manifests for each of the different services that we've seen. So we can, for example, go ahead and modify the YAML files. And for the purposes of demonstration, let's go ahead and take a look at the add service YAML file. And there's a lot of YAML in here for deploying all the different parts that I care about for this Java service. But what's most relevant are actually the lines here from 47 down to 56. Basically, what we're doing is we are modifying runtime parameters for the JVM that we're going to be booting up for the ad service. So the first thing we're going to do is we're going to modify the command line parameters that are being passed into the Java arguments. So we're going to pass in a Java agent. This is a way of hooking in and adding instrumentation into a Java application. Now, OpenTelemetry publishes a jar file that you can use that has instrumentation built into it. And as mentioned earlier, Splunk also has distributions, just like many cloud providers and vendors today. So you could also take a distribution and plug that jar file in to add your auto instrumentation. So that's kind of step one, change the runtime parameters. Next here, we're going to go ahead and set the node IP address. This is so we can connect locally to any agents that are running on the host. In the case of Kubernetes, it's very common that you would use a daemon set to deploy this and have one agent per host. So once we actually have the node IP information, we can actually specify an endpoint. So the instrumentation knows where to send the data that it has generated and collected to. In this case, we're going to send it to that node IP address, and we're going to use port 4317. This is the native port that the OpenTelemetry collector is listening to if you're sending in native OpenTelemetry format, which is known as OTLP. So now we have runtime parameters changed. We have a destination that is configured to actually send this telemetry data. By default, it usually sends to localhost. In the case of Kubernetes and leveraging a daemon set, localhost doesn't work. You need the node IP address. And then finally, you just need to set a service name. So what do you want to call this service? So for example, in the case of distributed tracing, the traces, the spans that are being emitted, you want to go ahead and add a service name. The service name will be what you specify here. So we're talking about the add service. We'll go ahead and we'll specify the add service as its name. That's it. Now all I need to do is start this add service up, and it will automatically be instrumented using the jar that I've already provided, using the exporter configuration and the service names, and any frameworks that are supported. In the case of Java, many are supported. It will go ahead and automatically instrument the code for you. So I didn't make any code changes here to the Java application, but still I can get it to generate and emit telemetry data. Makes it very quick and easy to get started. And then you can see this in the backend or backends of your choice, or you could also just pass it through the collector and see it natively on the collector. We'll look more at the collector here in just a second. So auto instrumentation is a great way to get started. It'll usually handle all of your incoming and outbound requests from an instrumentation perspective. It helps from context propagation to ensure that you can actually stitch these spans together into a trace and send this to the backend that you care about. Now, we can also quickly take a look at a manual instrumentation example. So I had mentioned before that the cart service is actually a .NET application. So maybe we'll go look at the cart service implementation file. And here, this application has actually been manually instrumented. So you'll see, for example, it's using OpenTelemetry packages, the OpenTelemetry trace and context propagation packages. And then what ends up happening is that within the cart service here, we need to specify some parameters. So first, we want to go ahead and hook into activity source. This is the way in .NET that you can actually get to the instrumentation. And we're going to specify that we want to use OpenTelemetry.net. We can set our context propagation formats. So here it's using B3. You could be using W3C trace context, for example. And then if there are other parameters or other configuration things that you want to change, you could also specify it here within this class. Then from that point, it's just a matter of going ahead and instantiating the activity context that you care about. So you'll see down here, it's actually using the context propagation and the B3 context propagation that I set. And then for every single function or method within my code, I can tell it that I want it to instrument. So I can say, for example, here, I'm in the add item task, and I want to start getting trace information, and I want to actually set some metadata. So I'm going to set two tags, the component.rpc and the grpc.method. And you'll see that the similar behavior happens for all the different tasks that I have here. So empty cart, same thing. I want to start an empty cart trace. I want to set some tags for this. So basically, I need to instantiate the tracer information and the context propagation, maybe even the exporter if I want to specify that as well. I do that once typically per my application. And then within each of the methods, functions, calls that I care about, I would go ahead and update my code to actually generate the telemetry data that I care about. This is not too uncommon from how you would typically handle like metrics or logs within your application. I'm specifically showing you traces here, but the same basic concept applies of kind of hooking into your code and generating telemetry where you care about it. So OpenTelemetry supports all the major languages that you would expect. There's manual instrumentation for all of them, and most of them offer some form of automatic instrumentation, which makes it very easy to get started. And really cool, you can actually mix and mingle. So you can add auto instrumentation and then enhance it further by adding manual instrumentation as well. So lots of flexibility and choice here, depending on kind of the requirements in your environment. Now, if you're interested in learning more about this demo application, we have a forked version of it on the Signal Effects GitHub organization. Feel free to take a look at it and see all the other different languages that are supported and how you can get started with OpenTelemetry. Okay, next, I would like to switch over to the OpenTelemetry collector and show you how to get started there. So here I have downloaded the Splunk distribution of the OpenTelemetry collector. Again, you could use upstream or you could use other distributions as well. To kind of kick this off, I'm going to just start the collector up. I've already built it here locally on my system. So I'm just going to start the OTel collector command. And this actually fires up all the configuration options here. So you'll see like exporters for OTOP and for SAPM and signal effects all being enabled for you out of the box. Because this is the Splunk distribution, it has been optimized for that, but it is easy to customize as you need as well. And for the purposes of demonstration, I've actually gone ahead and enabled the logging debugger, so you can actually see it collecting and processing and exporting metric information right out of the box. So just by firing up the collector with the default configuration here, I'm actually getting local system metrics that are being generated and processed. Like, for example, I can see memory usage in here. I can see CPU load average. So all of this is happening automatically by the host metrics receiver that comes as one of the receivers in the OpenTelemetry collector. So very easy to kind of get started here. And then you can plug in your own configuration. And depending on the requirements of the data and how you want to handle it in your environment. Actually, I would like to show kind of how you would get started with actually building one of these. So for example, I will just create a test YAML file and let's go ahead and kind of build a collector configuration here live. And we'll start with something kind of very basic. So as mentioned before, there are many different components of the collector. So one is receivers, kind of how you get data into the collector. And I'll use a Zipkin, which is a trace receiver that's available. And I'll keep the default configuration. So it'll use like default ports. And then I'll also define an exporter. So here I will use a logging exporter so we can see it on the console, just like you saw before for metrics. And I'm going to set the log level to debug so we can actually see verbose output here, the actual payload itself. So you can see what's actually happening in the system. And then I just define a service with my pipelines. And because we're using Zipkin, this would be a traces pipeline. I need to specify what receivers this tracing pipeline will use. That will be just Zipkin. And then which exporters this pipeline will use, which in this example will just be logging. So here is a very, very basic example, a single receiver, a single exporter with a single tracing pipeline. Of course, this YAML file is extremely flexible. I could have multiple different Zipkin receivers if I wanted to. I could define multiple different tracing pipelines if I wanted to. I can also define metrics pipelines and logging pipelines. But I'm just trying to keep it kind of simple here so we can kind of see it live and see how the system behaves. So that's it. I'll go ahead, save that file, and then just like before, I'm going to start the collector, but here I'm going to specify a config, and I'm going to say use this test.yaml file that I just created. So now you can actually see that it has enabled a Zipkin receiver and a logging exporter. So it's basically taken the new config that I've supplied to it. Now on the bottom here, I actually have some example data. So I, for example, have a payload. This is a Zipkin payload in JSON format. It's actually a single span trace. So not anything too exciting, like it's calling some endpoint called foobar. It has some metadata in the case of tags in here, actually some interesting tags. We'll come back to that in just a second here, but a very basic payload. I'll just reduce the size here. And what I want to do is I just want to send that payload to the collector. So what I'm going to do is I'm going to post that payload. It's the same exact JSON file that we just looked at, and we're going to send it to localhost on port 9411. That's the default port for Zipkin if you're not familiar with it, and the default path that Zipkin is listening on. So I'll post that data on in, and you'll see that that single span trace is now represented in the collector, and it's actually been printed to the screen because we have the logging exporter on. And you might remember it had like foobar, and it had some attributes or some tags, and some of them were a little bit questionable. They show up here as well. So this kind of proves that I was able to send a Zipkin payload to the collector. It could receive it, and then it was exported out, and I can actually see that locally, which is pretty cool. Now, if you actually look at the data here, some concerning things like social security number, which I hope no one would ever add to their telemetry data. But for the purposes of demonstration, you definitely don't want to be passing that. So like, how could I get rid of it? Or even user information, like email addresses could be sensitive. Do I really want that to exist? Or do I need that for any specific like troubleshooting or observability purposes? Who knows?
So what can I do about that? Well, I could come back in to my example YAML file here, and I can actually create a processor. So let's use what's called the attributes processor, and I can define a variety of different actions. So I could say action, for example, I definitely want to go delete that social security number tag because that is sensitive information that should definitely not be sent anywhere. I probably also want to do something about the user field. So why don't I hash it? So it might still be meaningful to me. I might want to aggregate based on hashes, but I don't want to actually leak the email address. That wouldn't be great. And then finally, maybe I want to insert a new key value pair. So maybe I will say conf, and the value here is going to be reinvent, right? Because we are at reinvent. Now that goes ahead and configures that processor. I then need to enable it in a pipeline. So I'll just add a processor here. We'll call it attributes like it is defined above. And that's it. So we'll just start the collector back up. There it is, it's running. And let's send that payload one more time. And what you'll notice is, hey, social security number, no longer here. That's great. Hey, user has now been hashed. So I don't know what that value is, but I could still like aggregate and get some useful information out of this. And then I also have this new conf key and it says reinvent. So the collector received a specific payload, but it made modifications to it before it exported it out. This is the flexibility that the collector provides to you. It's all driven via YAML. I'm showing you very basic examples, but it can do some pretty complex and impressive things kind of overall. So as you can see, it's really easy to get started with OpenTelemetry, whether it's instrumentation, auto or manual, or data collection, whether it's traces, metrics, or logs. You've seen a little bit of everything here. And of course, this is just the tip of the iceberg. There's a lot more to this project and a lot more that you can do. Go ahead and take a look at the OpenTelemetry IO documentation or the GitHub READMEs. There's lots more information and things to play with. If you're interested in seeing more of like a demo environment that you yourself can play with, I have a bit.ly link that you can go hit for a workshop. The slug that you want to enter is Splunk-OTel-workshop. So Splunk-OTel-workshop will get you to a repository that has a Docker Compose that will help you fire up a few applications using OpenTelemetry and the collector as well. So be sure to check it out.
All right, so you just saw a demo of how you can get started with OpenTelemetry. As you can see, it's really quite easy, it's flexible, and you can use it however you see fit to kind of meet your business requirements. Now, of course, we can only show you like how to get started with the project, but we would love if you got involved as well. So from a next steps perspective, this is fully an open community. You can get involved today. All of these projects that you saw, the instrumentation libraries, the specification, the collector, all of these are represented as GitHub projects, and you can actually get involved today. There's GitHub issues in these repositories. Good first issue or help wanted labels are there to kind of help you understand which ones you could jump into today. Each of these projects also has what's called a SIG, or a special interest group, and they usually have very regular meetings once a week or once every 2 weeks. Everyone is allowed to kind of come in and get involved with that project, to ask questions, to ask for help, to help influence the roadmap and kind of next steps. There's also a very lively conversation happening on Slack. It's part of the CNCF, or Cloud Native Compute Foundation, Slack instance. You can search for OpenTelemetry or OTel, which is the abbreviation that is used. So really lots of ways to get involved in the project. You can find lots of YouTube videos online, as well as conference talks or even blog posts about the project from anyone, from cloud providers and vendors to also end users. So we see a really broad adoption across all of the industry, and we would really love to have you get involved with the project as well. So take a look at it. We hope you enjoyed this session, and see you online.
See you soon. And we're super happy to share more about OpenTelemetry in the future. One thing of note, OpenTelemetry is a massive project. I think Steve mentioned it's the second largest project in the CNCF by number of contributors and by contributions. Splunk is certainly not the only vendor in it, though we're one of the larger contributors. It's something we're very proud of. So you can use OpenTelemetry of our solution as well as various others. So thank you very much, and we'll see you in the community.